Well, welcome everybody, 1 p.m., March 30th, to the Propeller 2 Live Forum. A couple topics I took note of, which were just mentioned, were Stephen has a small update about something, maybe VSC or P2P2. Chip mentioned PLL best practices, and we think Bagger might show up a little bit later too with Pheonix. Are there other items that are on people's minds of any kind? Support related, application, product, ideas?
Ken, this is John.
Hi, John.
I've got a couple of things that I use for prototyping that I could show people.
Oh, good. Maybe we should do that first while people filter in.
Yeah, okay.
Are you ready?
I am, sure.
Cool.
Always ready.
All right, and then we can move to Stephen and then PLL, and then Baggers might show up.
All right.
Does that sound about right, Chip? You said a little later he'd appear?
Yeah.
Okay. So,
Shall I take it?
Yeah, you can take it.
Okay. I work a lot with middle school kids and kids in general. And when I'm introducing them to digital electronics, we use solderless breadboards, but it's kind of a pain when they have to set up 4 or 5 LEDs and the dropping resistors just to see some things. So I made up some little modules, and I'll show them to you here. I think you can probably get a pretty good view of these. These are things that plug into a breadboard, and I've got one down here that's just 8 switches, logic 1, logic 0. I got another module here that I think that's 8 LEDs on a shift register. And the reason they're on a shift register is because the microbit computer does not have 8 contiguous IO pins. So this allows students to shift out 8 bits if they want to see a count. This module is 2 debounced push buttons, and I also have 2 debounced switches. This upper module is just 8 LEDs, and I've got a ULN, I think 2803 or whatever it is, 8-bit driver. I've made up these little modules that allow people to put a wire in here. This is just, I forget the name of the manufacturer, but these, you just push them and you can stick a wire in there. And so the kids can put a temperature sensor or something else in there. I've got another module, I don't have one right now, but it's very similar to this with the push buttons on it, but instead of push buttons, it's a debounced switch. And I also have made up this little module, which is a logic probe. You can put power and ground in here, and you can see a logic 1 state, a logic 0 state, and you can also see a pulse, whether it's a positive going pulse or a negative going pulse. And these things are, I put them all on one printed circuit board layout, and I'm going to get Gerber files of these. If anybody's interested, I could pass them on through Ken, but this is about 15.5 centimeters by 6 centimeters, and I send them out to OSH Park. And when they come in, a friend of mine has a shear, and we just shear them up. And I've got another friend who likes to solder SMT devices, so I give him all the parts and send them away and buy him lunch about a week later and get these back. So I just found them very handy, even for my own breadboarding, when I need some LEDs or I need switches and push buttons and things. So anyway, I share that with you. And again, I'm happy to share the Gerber files.
Questions on that? Is that all through hole soldering then?
No, it's mostly surface mount. The only thing that's through hole is really the pins that go through. Let me just get one out of the breadboard. There are pins that go through that you can see on the bottom here that go through to the breadboard, and there are pins that go through for some of the connectors. I solder a little plastic standoff on here so that when it's on the breadboard, you're pushing the switches, it's not flexing down. It just stays up about 11 millimeters. So there's surface mount, the ICs and most of the components are surface mount, except where I have a resistor array on the board, and that's a through hole. So it's a mixture.
Middle school or elementary?
Middle. Yeah, hey, it's grades 7 through 9.
Hey, John, how do you show that one board that shows like high, low, or low, positive or negative pulse? Do you use some LEDs to represent that?
Yeah, I've got LEDs on here, Chip. We've got a red LED for logic 1, a green LED for logic 0, and a yellow LED for a positive going or a negative going edge. And I've used a comparator to sense the logic 0, logic 1. And I use a dual 123 multivibrator to detect the positive and negative pulses, and then OR them together with a couple of diodes to flash the yellow LED.
I see. I see. That's pretty good.
Now, the problem today is that the breadboards do not have the power and ground strips on them aligned, the holes in those aligned with the holes in the breadboard itself. Otherwise, you could have pins on the bottom here that would plug into the power strip and pick it up. But I use these 2x2 modules on here that will accept wires. And the nice thing about that is you can daisy chain it from module to module, and you don't have to take up space on the breadboard itself. So
Yeah, that's funny. They didn't design. I'm looking at ours here that these side strips that run perpendicular, they don't line up to the grid.
yeah, they don't. The one that I've got that I just showed you was made probably about 50 years ago by a company called AP Products in Ohio. And AP has all the pins that line up perfectly between the breadboard and the power, you know, so that that would make it easier, but they don't on this one. Also, their pins are gold plated, and it's very easy to stick those pre-made jumpers in them, or wires as well. But that's a very nice breadboard.
Interesting.
John, we have a tool called Cyberscope, and I'm pasting a link to a Google document in the chat. And if you go to slide 3, you'll find a bunch of links to drafty tutorials that are created with Cyberscope. So I thought it might be a good way to plot all the digital stuff.
That's good.
And it runs in a browser. It's made in JavaScript. So you just close the print. You include a module called multimeter, and then you close the terminal, and then you open Cyberscope and it graphs.
Oh, that's good. How many traces can it graph at a time?
I see 2 in most of our examples.
Okay. All right.
So maybe that's useful.
I have a Sele logic analyzer that I've used too. I haven't shown that to the kids, but
this also does analog. So you can take 2 analog inputs and then measure voltage over a resistor, LED, or whatever.
Okay. I mentioned before that Analog Devices puts out a module for students and educators that it's a function generator, a signal generator. It's got a logic input, many logic inputs. And it's just a nice device, a little expensive, but it's nice to have. That's
very cool. You know, it's funny. I just got off of a call a minute ago with the organization we work with, cyber.org.
Yeah.
And they're, you know, the microbit is everywhere now. So they're trying to find a way to introduce breadboarding with microbit to a younger audience. And we're discussing something along these lines of just taking the box and making a robot.
Yeah.
Because they're not, a lot of groups are not keen, for good reason, on using the plastic STEM learning toys that are really awesome engineering, but they're totally closed up.
Yeah.
It's funny because we give them all the capability of the most awesome robots in elementary school, but what changes is the system opens and then they're eventually coding it by high school. But what it does is kind of the same.
That's interesting. Well,
so yeah, it creates like an upside down funnel of who's really interested when reality hits with learning.
Yeah, that's good. That's good. Well, with the kids in the middle school class, I have wired up a number of the TMP 36, I think it is, or 35 temperature sensors. And we've got some adapters they can plug right into that. And I also put some together with clip leads on it so they can attach it. And the kids were just astounded that this little tiny computer could actually measure and display temperature. And when I hit it with the freeze spray and it got down to minus 44 degrees C, I mean, it's just fascinating, just absolutely fascinating. So they can hardly wait to get their hands on servo motors.
No, yeah, it's really cool. And, you know, it takes someone like you to go in class usually to really get all this. The teacher does not have, we're training them, but they don't have the expertise yet. It takes years.
And that they don't have time.
They don't have
They
time.
don't have the time to prepare it.
But interesting where you are in Utah. Are you in Granite County?
No, I'm
No?
in Salt Lake County.
Sorry, several of the districts have passed CTE standards on top of the state standards that require physical hardware.
Yeah, I
teaching
think we're
coding.
getting to the point. I'm on one of the boards in the school district, not the school board, but there's a foundation board and trying to push them in that direction.
Good. Cool stuff. Thanks for sharing. Now, if anybody wants what John has shown us, he can put together the package. I assume he's already got a BOM and Gerbers and OshPark files. We just don't want to waste his time, but I've seen a lot of things like this. And so it might be a good idea to just produce them too.
Yeah,
It's
I'm
interesting.
happy. It's open source as far as I'm concerned.
Cool. Any more questions for John?
I've got a question for you, Ken. You mentioned about school kids and teachers. My daughter teaches 5-year-olds in a private school in England. She's got twin boys that are almost 7, and she's just started to teach them to solder. Now, you might think that's rather funny for a daughter to teach them how to solder, but my kids have been soldering since they were knee-high to grasshopper, and they've done it professional in their high school. They had jobs hand soldering at a production plant, so they're used to all of that. I've always been keen to try and get my grandkids into it. I've failed miserably with the other 6, but these 2 seem to be interested. And I just wonder how you go about getting the kids interested in it. Most teachers don't have the time, the wherewithal, the knowledge, etc. But my daughter does. And so I'd really like to get her to get the kids interested in it, and she could take that on board and take it to school. Just how do I go about trying to get their interest? What do the young kids really like?
So 2 things, one of them being storytelling that goes with it, and the other is the use of craft materials. So milk containers, little cheapy servo motors, and some LEDs. And then the make code tool that's available for microbit can achieve what you want. And there's really a lot online you can look for with this, but the microbit's pretty good with alligator clips. So it has these big wide pads on it, and you can connect an alligator clip to an LED or to a motor quite easily. And there's a whole bunch of stuff available on Amazon, cheap hardware that you could just drop ship to them. You just want to make sure it has a simple physical interface to the microbit. And then craft supplies and the make code tool. And if they can read, they can do it.
Right. Okay. I shall try.
Contact me offline. I'll give you a few links too.
Okay, great.
They're
Thanks,
at the
Ken.
age, sure.
And Ken, if I could take a minute, I'll show the chapter 1 through 3 of Andy's book
Please.
in a 10-second snapshot.
Let's do that.
Mhm.
So everybody's always wondering, how to get teachers up to speed. And Andy Lindsys' book with the chapter 1 through 3, what's a microcontroller?
Yep.
I shortcut that for hour of code with teachers with this little traffic light. And you can see my block of them here. I did an order of 300, got it down to 40 cents. And with that, you're teaching a little bit of soldering if they want to. A lot of times I go in and do an hour of code with a teacher's class and leave them with a dozen of these, and it's all plug and play. So within a couple seconds, plug them into the screen, they're off and running. And let's see, can I share my screen? Is that allowed here?
Very similar to what John was showing.
Yep. So here's a plug and play with a whole bunch of basic stamps. And the schematic is so simple. If they have any electronics or science knowledge, they can follow the schematic and they're off and running. So like I say, there's chapter 1 through 3, digital input, which is a third chapter. There's a switch on here. So what we're looking at is a regular traffic light, green, yellow, red, and the button, which simply comes down to a pin. So they have to add to their code, not just sequencing the lights, but interactive. When someone pushes the button, it acts like a pedestrian light and the white flashes, and hopefully they go to red, not green, so they can be pedestrians, not targets. So like I say, that's what I use now, is kind of an hour of code. And like I say, I've left hundreds of these all over the states and still going strong. My students solder these up under solder training and we give them away. And fully bundled, you're looking about 80 cents.
Wow. Looks like we need to get these things into a parallax form factor or formalized as products people can build.
Yeah, nice little plug and play test kit.
How did the teachers like it all?
Yeah, I'd say probably 50% of them truly implement. And the issue we get into is compatibility with Arduino and Raspberry Pi. I do have to change a couple resistor values because of internal resistance on the Pi. So I end up with a little too much resistance in the circuit, but a couple of shunts takes care of that, and they just modify it when they build them up.
Have you found as an educator that any teachers are moving from the Arduino to the microbit?
I have not seen that in my area, no.
Yeah, I've seen a few of these, which is kind of interesting because the microbit, not being the most capable embedded processor, has so many other good things on it they really like.
Yeah, the new Pico, I've got a couple of them that are asking about that and looking for a seminar on the Pico. That's the new $4 Raspberry Pi.
Yep.
Ken, this is John. Again, can I jump in here? Just a couple of things on the microbit.
Yeah.
One of the things that I found is when the kids attach their clip leads to the microbit, oh, my cat. Yeah, when they attach the clip leads to it, they can put them through the large holes, but sometimes they don't, and they try and put it on the edge connector, and they tend to short it out with the nearby connectors. So I made I 3D printed this kind of a little arrangement that will let the board slide in it. And if I don't drop it, you can see here, it only makes certain of those, the large pads available to the kids. So once this is on there, they can help turn it around. So it's like this, so the kids can also see the LEDs, but it only allows them to hook to ground +3 and the 3 IO pins that we use for a lot of experiments. And I can send you the STL file for that too, as well as I've got a little stand that I made too, 3D printed, so the kids can actually have this up on their desk when they're experimenting if they want to. Now, granted, here you don't have access to the pins, but when they're doing the experiments with the LEDs, it makes it a little easier for them. And if they're working in a group, to see rather than having to bend over and see it flat on the desk. So I can send you this file set too.
I'd like that. I'd like to share that out. Good solutions for sure. Speaking of the Propeller in education, we're getting a few more of these out there. I'm sharing a letter I just got back from a student. Through the Future Innovators Fund, we had a teacher suggest that we send a P2 developer bundle to his high school senior, who received it with enthusiasm. And he said, "What's the spin stuff?" And then he looked at it and he said, "Oh, it looks easy enough. I could learn it." And so, yeah, his brain is still open to learning new things. So looks like he's going to go for it on his way to college. So bring in more kids. Hopefully he'll be on our P2 forum soon.
Very cool.
I hadn't had much luck with those kids here around. It's not about the money. I have enough parts for them, but I tried with 5 different ones, and somehow they are not interested. Not at all. I don't
Ken,
know
if you send
interest.
that young fellow a email telling him about these, he probably will be here.
Yeah, I'll invite him over for sure. Yeah, and I think too in May, we're trying to invite in some mechatronics professors, and we hope to have a mechatronics oriented P2 forum, because we have one in particular who's doing very amazing stuff right out the gate in January, bought everything we had and made those trainers that I showed, and he's very productive. So we'll have him come talk in May. Just have to let him get his semester mostly over with.
Jonathan, how do
Yes,
you
ma'am.
keep your cat from walking across your keyboard?
I don't.
Oh,
Yeah, he's a pretty good typist.
yes, they are. Unfortunately, they don't speak English.
I have a narrow desk, so there's not much room for the cat except in my lap.
Oh,
She
I've
never-
got
she
3
never lacks for
laptops
attention.
across a big space,
Yeah.
and she just hops from one to the other. At least she stays off the 3D printers because they're hot.
Yes, mine hasn't shown any interest in the 3D printer, probably because of the noise it makes, or maybe the smell.
Yeah.
Well, some cats seem to like the warmth from the lower element on the 3D printers.
Oh, I do have a question that's pertinent to what we're talking about. Email or sending the whole things to Ken for the seminars he's doing in April of the butterfly bot that you saw recently that I'm working on. But I'm wondering, which pair of wings do you guys like? The blue ones or the yellow ones? I can't decide which is going to get. These will get to the girls,
Yep,
and these
I
will get to
feel-
everybody.
agreed.
Kind of wondering what you guys like.
They both look pretty good.
Yeah,
And
go
multiple
full color.
Graphics look good.
Yeah, I'm going to put in the tutorial I'm writing how they can make them easily
Nice.
both sides of the paper, so you have a really pretty looking flapping wing.
Maybe you could send both sets down if I don't sound too greedy.
Oh, I can send the extra set of wings, the ones I
Okay.
don't put on the bot. And then there's a kitty bot too.
See, Ray, she's kind of filling in what I was describing earlier. Make it move, color, light, some art, and then wow.
Well, I know these appeal to kids because at Robothon, they brought crowds of them around my desk, and I had quite a few robots every time. This is the main part of the butterfly bot. See, it has little feelers here that are going to flash. And then with the microphone, the one that's used with the Cyberbot, the passive one, it's going to make stridulation. So it sounds like an insect. And I've got that pretty down pat on how to do that. And then of course it'll be guided by a ping, and it walks instead of rolling. And when it walks, the kinetic energy of the walking from the crawler kit, because it kind of goes boom, 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 makes the wings flap. That way I don't have to have an extra servo on there for the wings. So it's pretty simple to do. So that's another reason why the kids and the teachers like it, because it's very simple to make.
Thanks for helping me out with that.
Yeah, everything in it is PLL products. I even use your little pieces of wire that you send us, the little bags of wire. You just twist 2 together and you get a really good shapeable antenna base for it. They can move these antennas into pretty much any position they want them in.
That's going to be
Oh.
fun.
Yeah.
And just tell me briefly, did you get the timing worked out? Have you gotten back to that?
Yeah, I'm having more success with it, and I've figured out a program too that shares what all the things I want it to do in a way that looks natural. So I'm surprised how well it works with the walker feet.
Yeah, there's a bag
Yeah.
of those coming to you too.
Oh, is there? I just asked for tips.
Carol was she was stuck between the what the microbit can do alone versus what the Propeller coprocessor is doing on there. And so we had to dig around a little bit to get her unstuck.
Well, one of the things I found out worked pretty well is, like you were telling me, the walkers are being run by the Propeller, the servos for the walkers, and then the feelers and ping and that are being run by the microbit.
Yeah.
So that works out pretty well. And you asked me about the servos on my giant spider. This is what they are. They're 60K. So those are heavy duty servos. Real heavy duty. They're from Senjin.
JonnyMac is working towards what was the protocol, John, for the servo? Are you even here today? It's not a Dynamixel, but there's another servo that's a real beefy gear, metal gear feedback position.
Yeah, it's a lower cost, similar kind of thing called the LX Tech 16A.
Yeah, these don't have any real feedback. They're just kind of standard acting servo. They're just Herkimer big.
Yeah, it's called from a company called Luan Sol that makes, so they're like lower cost Dynamixels, but they have really good specs. So they can do 240 degrees in servo mode with an absolute position encoder inside of it. And it's a half duplex serial protocol. So if they're on a network, it's just one wire to talk to as many of the devices as you want. And they can also go into motor mode, so you can do continuous rotation.
Yeah, I found out through Banggood and AliExpress and Senjin that the quality of the stuff I've been ordering is pretty good. So, and so much cheaper. You just have to wait a long time to get it.
Yeah, there's been a couple of times when things have showed up in my mailbox and I think, what the hell was this? Oh yeah, I ordered that 6 months ago.
Yeah, right.
But I got these from Amazon on a whim. Just somebody pointed out, because I have a good friend I've mentioned many times. My friend Rick works in the movie business, and I've written a couple of Dynamixel drivers for him. And these are like Dynamixels, but they're small, granted, but they have really good specs and they're very low cost. They're about $16 or $17 each. And they're intelligent. Again, they're on a little multi-network. So I've worked with them a little bit. When time permits, I'll write a full driver for them because I've got some robotic ideas that I want to implement.
Yeah, I've worked with them. I have 3 Robotus humanoid type robots, 2 of the small ones and 1 of the bigger ones. And they're all Dynamixel, all their servos.
Yeah, I wrote what is their primary one was, what did they call this small servo? I can't remember what it was. I had done for a company that made camera controls, not my friend.
Oh, yeah.
But another company, we had done that. And then my friend Rick, he makes big robots for movies. And he's working right now on all the Star Wars TV shows. And he called me up about a year ago and asked me if I knew anything about Dynamixels. And when I went over to his shop, he had Dynamixels that were the size of motorcycle batteries that cost a lot of money. But they used those in a multi-arm robot that was really, really neat. And he was able to control them with the propeller. And Luckily, those particular Dynamixels use RS-485, but sometime back, I had made a little board that plugs into the XB socket of the activity board that is RS-485 output. And so I gave him a couple of those. He plugged those into activity boards, and then he connect that to the RS-45 network, to these giant Dynamixels. I had to modify my code so it would work with half duplex open drain or with RS-45. It wasn't much of a change, but it worked, and he was able to show the bosses, okay, here's how the robot's going to move. And that robot did its thing in a Tom Hanks movie that is yet to be released.
The closest I've ever gotten to Showtime is I did a big spider bot that dances for a ballet show. I also had Ken's robots in there too, but the little girls got scared of them.
Well, let's move into some more P2 stuff because we have a lot of P2 brains hanging around here. Should we do Steven's topic first?
Sure, I'm ready.
All you. And we'll come back to future presentations in a minute because JonnyMac has more to share.
Okay, so while I'm setting up a screen share, I released an update to the Spin 2 support for Visual Studio. I had found out that I missed the receive method pointer, and so that's now included and highlighted correctly in the latest update. I went back to the matrix panels, and what I'm interested in doing now is measuring the light output for different values, because LED panels are notoriously difficult to control brightness. And my goal is at least a good 16 grayscale value for all the LEDs so we can get some really good colors. So I needed a way to measure them. And so I'm at the first part of this project. What you see is the measurement brackets where I have BHG 1750 ambient light sensors. They are I2C devices, and they're small circuit boards bought from Amazon. You buy 3 in a group. And so I created a mechanical shell. When you're measuring light, the last thing I want to measure is my ambient room light. I just want the panel, and I want to block out the room light. Rather than having a dark room, I just decided to build this shroud and then clip it to the panels. And so I, with a lot of careful measurement and a little bit of work this past week, I came up with that design. And then this is what it looks like. There's a BH1750 board, I2C controller board. And it bolts in and avoids the circuitry pretty nicely. That's what the inside of the thing looks like. On the interior dimension, this is 24 millimeters by 24 millimeters. Point of which is I can play with 2, 3, and 4 millimeter pixel panels and have full LEDs within the chamber. When I put the boards on, that's what they look like. And basically it's a clip holder for to hold the shroud tight to the panel, and then another clip to clip these holders to the top of the panel. And so that's what they look like when they're mounted. Came together as 2 or 3 prototype runs on the parts, and then finally realized that one more change and I was able to make all the parts. So I don't have much progress other than we're ready to wire it up and try. I have the object created for the BH1750. And so I'm ready to put together the wiring harness. The way these will work is there's an address line for each sensor, an enable line, and then a common I2C bus. And so I'll be driving the I2C and the enable lines from the P2. I'll be driving the matrix from the P2. And what I'll be doing is stepping through all the different PWM values, understanding what the different settings are. And the goal is probably a new PWM design. Right now I'm even duration phases for the PWM, and that's probably not appropriate for the LEDs. And so I'm going to find the 16 steps that I want to be at, how to drive it, and then design an appropriate timing for each of the PWM phases. Probably something closer to linear or logarithmic. I'm not sure. We'll see what it comes out as. Did some experiments with a 4-phase PWM that is different widths between the phases. and that stuff works really nicely. So that's where I'm heading, and that's what I'm working on. Just thought you guys might enjoy seeing how I'm going about doing it.
That's a neat idea. Can you go back to the little board that had the sensor? I couldn't identify what part on there was actually receiving the light. And is this thing just doing brightness?
Correct. It's this guy right here. And
Okay.
he's a BH, it's a 6-letter, 9-letter part. I had looked it up.
So does it, I mean, different wavelengths might register at different intensities for the same energy level, right?
Correct. And so I tried to carefully select the part that would handle the LED wavelengths and the brightness. It's got 3 different measurement techniques. And so very quick measurements to much longer term, higher resolution. So 3 different resolutions of measurement. I believe this falls well outside what I care about with driving the LEDs. But I'll know shortly once I get to testing. I'll also have a BH1750 object built on John McPhail's I2C object, and that anybody can use should they want to go down this path and play with these sensors. There you go. Ken just put up
you might have to do some like coarse calibration just to set the the extreme limit by looking at, write a pattern of pulse widths to your RGB LEDs and come up with what looks like a good white.
Correct.
As the distal end. And then turn off, and then vice versa for the other 2, and then measure what those levels are on that thing, and then you can work it backwards.
Correct. I'll be doing single color for grayscale, and then also the combined colors. This will also lead me to the panels by nature by design are intended to kind of blend, kind of set the levels for the colors appropriately so they're equal. I'll also be able to tell if that's really true. Reds, blues, and greens are radically different brightness without adjusting them. And so I'll be able to sense all that and play with it and see what the colors look like. But this is not frequency measurement. This is just lumens, if you will, being measured.
Right. Yeah, these LCDs and all these things we look at are funny because as soon as you go to put a camera in front of them, the color changes drastically. Like these cheaper LCDs tend to look blue.
Yes.
Not to our eyes, but through a camera they do.
Correct. You've got much more accurate sensing. And my photographer son is all over that. That's why he has color profiles for every single sensor he's got and lenses and things. And
yeah.
His drone cameras have different profiles than his handheld. Yes. There's a reason for that.
Yep.
So a little bit of progress and things I'm working on lately.
Good. Now, when we left off, I was going to go fix the batch file so that I would check if a file exists so that we wouldn't leave someone high and dry if it didn't.
Correct.
I have not been able to get back to that. You think that was like an hour away when we got off the call last week, but I never have gotten back to it because this stuff came up with the PLL.
No, that's
jitter, and so that's just taken all the focus.
Nope, I prefer you stay on the PLL. I've got the batch file all worked up here. I'm just doing final testing. I'm also testing setting the path environment variables so PNet can be found without an absolute path, and the same thing for FlexBin. And so I'll be putting those recommendations up in my task GitHub for setting up Visual Studio. And then I'll work with Ken and we'll get the quick bites set up. At the same time, I prove that file out. I'll send you a copy of it. You can just include it in your next distribution.
I have a brief question for you, Stephen, before we get into PLL. So you made a new VSC extension?
I updated it, yes.
And I've heard you talk about this. When you open up VSC, if it doesn't say a new one is available, that's because why? And then how do you update it? Didn't you mention this?
Generally, only the first time. If you had hand installed my extension before, it may not see the new extensions arriving because they're built under a different developer name relative to how VSE sees things. Once you have my extension installed from the store, you should never have the problem of it not telling you about an update.
Are we on version 1.0.1?
Correct. That's the latest.
It's working and I didn't even know it.
Oh, sorry.
That's normal for me.
Yeah. It's good because when we had our discussion last week about the method pointers, I always, as we're talking about this stuff, I review the documentation simultaneously while we're talking through it. And I found the received method pointer was just not covered. It's like, oops. And so while we were in discussion last week, I put in the code, but then I didn't release it, thinking I might find other things between then and now. So I released that within the last hour. So you've got the latest.
Oh, very cool. And I'm actually running any code that I post as quick bites on this and on Peanut.
Nice.
Before I post it. So yeah, I'm looking forward, since you have the light sensor, the lumen sensor, the BH whatever, I wrote it down.
BH1750.
Yep. And there are a few good things coming from JonnyMac. So I've stalled at the moment because of other responsibilities, but look forward to this.
Right. I will go ahead and as soon as I get the sensor object is working, and as soon as I wrap the interface, I'm setting it up so I can install 3 of the objects simultaneously, each with their own chip setup, each with their own chip select line. And as soon as I get that all proven out, I'll go ahead and submit that object to the P2 OVEX as well.
Thank you.
So we'll have it there.
Well, shall we move on to PLL chip?
We could, or Jim just popped in here. Jim, I know it's late for you. Would you want to talk about this last thing you made?
Yeah, can do. People may or may not remember it from back in the day, but we added a little bit of extra because I know it was one of Chip's favorites. So as the game was an 8080 game, I decided to get Pheonix working. And
so Pheonix used 8080, huh? Here
well,
it is.
it's an 8085.
Anyone remembers this? Let's see.
I'll spot your video, Chip.
Oh, it's too much glare in here.
Oh, wow.
Does anyone remember this game? I used to go collecting on the paper out, then throw all the quarters in this machine and pay the bill later. This was the mothership that you have to shoot all the way through, then you have to shoot through that band. Anyway.
So yeah, it was, we can't have that on the 8 cabs version because the graphics are basically, there's no sprites in the game. They're just 2 tile maps, one with a scroll, which has the background space and the mothership on, and the other one has the main character and bullets and stuff. So it's too intensive to put in one cog, as well as the emulator and everything, like with the Space Invaders emulator. But it will work with a single prop. So when we do the single cab, it'll be able to work in that.
Yeah, by cab he means cabinet, like a standalone.
Yep. Okay,
cabinet with the controls and the screen and the sound.
Let me just find a link. I'll put the link. We've gone on Coley set up a Hackaday project. So we can try and get some views on Hackaday. It's still in the early days with the cab, but where Coley's got his laser fixed and working now. So it's just a case of building a load of cabs and then testing them. So we're getting close to having the full set of 8 working, And
Yeah,
obviously,
that'll be good. Did he get his laser cutter
yeah,
working again?
it's like laser cutters working. He used one of the driver for it is done by a prop guy. Apparently, I can't remember his name. I'll have to check with Coley. But yeah, it was made by a prop guy.
Okay.
So small world.
Good.
Has anybody done Pong yet?
No, but I probably could do. Wouldn't be too hard.
What is that game, Carol?
Pong. That was one of my favorites.
Oh, Pong. Okay.
Yeah.
All right. I'll get a version for you, Carol. Have you got the
I think we can do 3 Pongs per cog.
yeah. Yeah, probably
One
could,
at a time is enough for my old head.
yeah, I'll get you a version for you. Don't worry.
Okay, thank you.
Are you pulling up something, Jim?
No, I was just gonna see what processor it was, just to make sure.
Pong. What processor Pong was?
Yeah. What was it?
You know, didn't Steve Wozniak design that in 44 chips? But
Yeah, a netlist CPU device. Yeah. I don't know. I'd have to. It'll be easy enough to do a version of Pong anyway. So I'll just.
oh yeah, that's same with Breakout.
Yeah.
I noticed a bunch of solved Rubik cubes behind you.
Yes.
Impressive.
Thank you. Yeah, I've had them for a while now. I've probably forgotten how to do them. It's been a while since I've done them.
I can mix them. Go
Yeah,
ahead.
yeah. And that's pretty much it, really. That's where we're up to. We've got Pheonix working for Chip.
Yeah, thanks.
He's a happy bunny.
Yep, I've got to find my other button board. I wish we could use this the arcade board because it has much better buttons that are further spaced.
Yeah. Well, the thing is, you've got the source there.
Yeah, I know. I could.
It'd be easy enough to change to add the 5-button joypad.
Okay, I'll try to do that.
Yeah. If you get stuck, give us a shout. I'll talk you through where it is in the code.
Okay.
Chip, I can send you mine if you'd like.
Your what?
Did you just misplace your button pad?
Oh no, I mean this little. Let's see. Let me move the camera over there.
Oh, I was under the impression you
This
lost
little
it or
thing
something.
here. You know, this is like the satellite board that goes with. Oh, I've got so much junk here. This thing. This is like one P2 edge with the 8 connectors that go out to 8 cabinets, so we can do eight simple games simultaneously over these things. But this is representative of what goes into the cabinet.
Yep.
Wow, great work. I'm looking forward to this.
Yeah, me too.
I wonder if I could do it on the Hydra.
Yeah, I'll make it work on the Hydra, I suppose. It's not that
I've
hard.
got one.
Yeah, okay.
I haven't used it in a long time.
Well, the Hydra was SX chip based, right?
No,
It
P1.
was
No, the
Propeller,
Hydra's
P1.
P1, yeah.
It's P1.
It's funny actually with the talking about the SX chip, but because I started doing like electronics stuff and TV displays with the PIC chip like years ago, and then I found out that it was too slow, obviously, to do anything color wise, and that's when I actually came across the SX28 first, but couldn't find anyone that still sold it. So that's when I found Parallax and the Propeller.
Wow, that may have been 20 years plus ago.
Yeah.
Yeah, I still have a couple in the connectors that go with them, but I've never actually ever used them.
No?
Never got around to it.
Jim, you wound up using NTSC and then that later code that I wrote for the video driver, right?
Yeah. Yeah, basically I used the newest at the time that I took it version of your display driver, the static one, and I took out all of the PAL stuff because I thought, well, there's no need for it for the cabinets because they're only going to be PAL or NTS. Well, they're only going to be NTSC anyway.
In my experience,
The
was
arcade
it
games are usually NTSC anyway. It's 60 hertz.
was it your thinking that NTSC is just less hassle and it looks a little better?
Yeah, it's a lot stabler. And then basically, I forgot where I was going. Nope, it's gone. He threw me with the NTSC being less hassle.
Yeah. Yeah, they should have just stuck with the American way.
Yeah. So anyway, I took the PAL stuff out to give me enough space in the cog, and then I included inside the same cog the driver for the ILI 3. Oh, hang on, which the 3 ILI 9341 LCD driver, but it uses the 16-bit data bus rather than the I2C or the SPI or whatever.
Okay, so that looks probably pixel perfect then.
Yeah, it looks amazing.
Yeah, because I noticed the NTSC when you have reds.
Yeah,
dim
it doesn't
reds.
like it. Yeah, it doesn't like it with a single pixel of red, does it?
Yeah, no, it needs
Especially
a couple pixel width. But you know what? Maybe we could
Yeah.
fix that by stretching it out a little bit. Because if you get your luminance
Yeah.
instance like less than or just equal to one color cycle or less than a color cycle, it can't resolve the color or the luma. It just
Yeah.
makes a mess.
Yeah, because I noticed you get some color bleed on the antenna on the UFO, the mothership.
Yeah, yeah. I noticed the red scores didn't look clear.
Yeah,
But I haven't looked at it on my analog.
Looks perfect on the LCD.
Yeah, that makes sense.
So Chip and Jim, are we going to make these as a product?
You're welcome to, yeah. Basically, Coley's gonna give away give you the details, measurements for the cutter, the laser cutter, so you'll be able to cut them, or if you want to make the caps as well.
And that would need the P2 arcade board and the button board, right?
Yes.
Okay, I'd love to do that.
Yeah, because
It's
then
just
you can.
necessary demo, if nothing else.
Well, the thing is, it'd be great for kids in school to learn how to do play with arcade stuff and program themselves with the P2.
Yeah, and I thought that was where you were headed, but I wasn't sure. We have these meetings every week where we're going through various manufacturing issues, and we don't know what you guys, what's going to become real and what's not sometimes. So
yeah,
I'm asking here.
We need to get all the hardware built, and then
we need to get it all built and before we can do it. All codes.
Prove it out, and it should be great.
Yep. I envisage having two classes of it, which is the 8-in-1, and that was mainly done for getting you guys seeing, because it's all running on one microcontroller, 8 arcade cabs. It'll get a Guinness World Record for you guys as well. So
they'll have to make a new category, right?
Yeah.
Arcade games might be something that really fit into STEM, because kids would love to do that.
Yeah. Well, the point of doing what I'd like to do is the single one as well, because then that way we can have a lot more of the cog free, because it's a bit tight with the emulator and the TV driver and everything going on with the 8-in-1. But if you have just like a single cog or a single board, you could have two networked together still, but there'd be separate props on them.
Still using the same hardware, right?
Yeah.
Okay. Well, I see Michael's hanging out here, so he and I will get together with Chip, and if there are no changes, we'll get these made.
Yeah, cool.
Yeah.
Yeah, that was the point for you to be able to make them and sell them if you wanted.
Yeah.
You know, since I've got the video renderer running in the background on a spin cog, so we could come up with some simple template and some graphic routines so that kids could actually make their own apps that could run on one cog, and then that would go out to run one cabinet.
Mm-hmm.
If you need to do any 3D prototyping of parts to put it all together in some kind of a console setup, I'm available for that.
Good to know.
Yep, thank you.
I think
I'm really good with OpenSCAD, so I can design something fairly well.
I believe Coley has it kind of laid out now, so that we're just we're gonna cut thin sheets of MDF, was it, or
it's ply? I think
ply would be stronger.
I think so. Yeah, I think it was ply.
Yeah, and then these cabinets glue together, and all the parts mount from the inside. Just buttons and a display and a speaker.
Yeah.
Well, you could do that then with something flat, like this is the this came with an instructional kit for microbit.
Yeah.
And so something like that, everything's just screwed to it. Here's your microbit, here's a platform for input, and then of course there's a breadboard here, but you could make something on that and everything's just screwed on. That would be simple and cheap.
Yeah. I'm thinking about all this educational stuff and what like Michael was saying, it's hard to engage kids. What happened is these things are like engineered to completely suck up all their attention, you know, so there's not much left. But if this thing were to disappear for some reason, they'd find electronics fantastic. And it's a great time to be into electronics, but this thing is really hogging up their mind share. I think part of the situation is that nothing's more really interesting in the end than other people. So this becomes a connector to all their friends, and then they have all these interesting things they do over it. So, but it's kind of like a drug. It just displaces everything. We have a daughter now who's 11, and she's just, you know, it's at this moment in time, it's just inordinately large in her life. The other kids kind of have gotten through it, and then they wind up deleting TikTok and other stuff, but she's in the thick of it right now, and she's the kind of person that'll probably stay there for longer.
Yeah.
Did you see how when earlier my daughter came in and she was all excited? I don't know if anyone saw her come in, but she said, speaking of cats, we have this cat that's been pregnant, and she said it just had a baby in the closet. So, and there's probably more coming. So all the kids are focused on this right now.
Noah's Ark. I'm not coming over for a while.
John mentioned in the chat that it'd be possible to do a P2 powered Game Boy like project, and that was one of the things that Coley and myself came up with. Basically, you can get I don't know if you can see that. It's like a Game Boy thing. The LCD's been taken out. It's what I used to do the driver, because it was an ILI LCD inside this, and so basically all we need to do is take the main board out, make a new one, and with the P2. Obviously, we could probably end up printing new cases instead of these, and just get the LCD directly anyway. But we're just using it.
I don't think you should use the Game Boy thing. Well, that's good for a lot of us older people.
Yeah, I know it's good.
Come up with something brand new and different for these modern kids.
Yeah.
It's got to look more like a Kawasaki motorcycle or something for them to be interested.
Kids don't like motorcycles anymore. We all found that out. That was the first thing I wanted when I was a kid. But these days, like where we live, people buy their kids these things, and you'd think the boys would be all over it, but they're really not that interested unless maybe a friend comes over and there's a social aspect. They'll go ride around, but otherwise,
Yeah.
strange as can be. I think because they lack the experience of having to pedal a bike everywhere. You know, that
could
gives
be.
great appreciation for motorcycles, but they don't. But our little girls like to ride these things.
When I was a young woman, all males knew something about how to fix their car or change a tire. Now they don't. They just don't.
Yeah,
I know more about
this.
cars than most
I hope
young men I know.
Yeah, I hope electronics doesn't become like the old guy in Scouts who's teaching knots to young boys and they could care less.
Yeah.
You know, here's how to whip a rope.
What do you use a rope for?
Right. Yep.
And it's another thing with having like one with the one cab, we could use the MicroPython stuff, which might be more kid friendly as well.
Mm-hmm. Agreed. I could talk about the PLL issue.
Yep.
Yep.
Let me
Thanks, Jim, for staying
yeah.
up so late.
No problem. It's not
yeah,
too bad.
thanks for all that, Jim.
It's
I'm
just
gonna
10 o'clock here at the moment because you started early.
I'll play Pheonix when I find my other little board. That looks great.
Yeah. I'm sure Ken will pass you one over.
While Chip gets going, Jim, so when we finally start to collect up all the resources, we'll need to be obscure about where to get some of the ROMs and how to use them, right? That's
Yes,
a consideration.
Very much so. Yeah.
Very much
Well,
so.
The thing is, on the cabs, there'll be a couple of games already on there that I've done. I might even put Pong on there for Carol. Then case of writing it in 8080 wouldn't be too hard.
Can you all see that picture?
Yep.
Okay, so this, so we've discovered a problem. I don't remember who discovered it. Was it you, Ray?
No, it was Roger in Melbourne. Roger.
Okay, so what happens is the way the P2 chip works, on every 4 pins, there's an independent power supply input, which is 3.3 volts. And pins 28, 29, 30, 31, that group of 4 pins, also because it goes right near the edge of the chip, that power supply pin also powers the crystal oscillator for XI and XO. It does not power, well, it does indirectly power the phase lock loop, but the way the phase lock loop works is it's done in 180 nanometer at 1.8 volts. So what I do is I copied the 1.8 volt rail and then made like a linear regulator to generate 1.8 volts from the 3.3 volts so that it's quiet. And that works fine. Our problem is that there gets to be a lot of noise if you're flipping, like we've made some test programs which are really brutal. They just flip P28 to P31 at like the max frequency, all high, all low, all high, all low. And this creates huge, like very short power draws, or current bursts that have the effect of sagging the internal supply lines inside the chip. So this right here is a picture of what the blue bottom line is the ground on the bottom of the cap that goes to the chip, and the upper kind of boxed yellow line is the 3.3 volts that goes to the power supply pin for the last 4 pins. And this is during this super abrupt pin driving where we're going all high, all low, all high, all low. So you can see my little cursor?
Yep.
See, there's a dip there. There's one. Every time you see a dip on the top one, that's when this huge current draw is occurring. So we don't really have, Ray was pretty convinced that we had some issues with our power supply, but the external supply is quite stable. And this was measured, if you look up here, at 8 gigasamples per second. This is a 1.5 gig scope, and it was maxed out. And so, and we have here, well, 10 nanoseconds per division. So you can see there's a lot of detail.
Chip, I don't consider that stable. I still think you need to check your power supply. I think the crystal is a manifestation of the problem. It's not the cause. But I just haven't had a chance to go back and pull my P2 eval power supply off and put a new one on it. I reckon that will solve the problem.
Well, what we did is we did piggyback the 4.7 microfarad caps with much smaller caps of the same form factor, and it didn't make any difference. But you can see
but your regulator can't handle it. It's the whole supply issue. It's not just the bypass, it's the bulk, it's the whole thing. I want to strip the regulator off that corner and supply it with a new 3.3 volt regulator that has a proper input capacitor on the regulator, the output capacitors on the regulator, and then to the pins. And I think you'll find that that will solve your problem, and it'll probably solve a lot of other problems. I've been concerned for a while that your ADC could perform better. You know, you might get another 1 or 2 bits out of it if you had a proper supply.
Well,
your supply is
would
not
be fantastic.
That's why I said to you, Chip, take my board and try it. While it's not the power supply that's going to supply anyone that really wants to push the P2, because I've just used linear regulators, and I've decided that 500 milliamps is the max. So because I don't have proper cooling and all the rest of it, if you really want to push 8 cores to their limit. But I really think that board ought to be quiet. I've laid out, you know, probably 100 boards, most of which were modems, and they require very quiet analog stuff, because if you go back to the 80s and 90s, the analog chips were terrible. And you know, I'd probably have 1 million boards out there in the wild. They were built. We built them for Apple as Apple branded modems. So, you know, I've had quite a lot to do with that, although I am far from an analog expert, but I don't have the test equipment to test it these days. You know, all my stuff's back in the megahertz ranges,
Right.
not the hundreds. I'd really like you to try that, because I'd love you to see whether we can get the ADC working better. Because if it's just a power supply layout, you know, I can help you with the layout. I do not believe your layout's right. I think you've got fundamental design issues in there, and that's what I've been trying to tell you. And
no, we haven't, Ray. I've been hearing your words. I know what you're saying, but I don't know that that's all that's wrong. Or that's,
it might not be all, but it's a fundamental problem. And if you've got to get the fundamentals right first before you can go down to the next ones. And
yes.
When you put multiple chips, bypass and bulk chips together, they combine and shift your whole impedance down. But they're there to do specific purposes. The bypass is there to quelch the spikes. The bulk is then there to follow on behind it and supply that bulk current. But if your regulator, and it's a common known fact that the regulators can't react quick enough. So that's why you have to have bulk capacitors on there. And that's why I've got a lot more bulk capacitors. I've got a string of 22 mics and then a string of 4.7 mics on there, and big heavy supply rails, because you can't use little fine ones, they don't work.
Yeah.
And so I've got this massive track, 2 sets of tracks running around my board, one for 3.3 and one for 1.8, and they're providing the capacitors directly into the pins. And
Well, that sounds like what we're doing though.
no, it's not. You've got individual little regulators. Now, I've not looked at your raw PCB files, but I did have a bit of a look when I got a few minutes yesterday under the microscope, and I looked at the little regulator. Now, I've been concerned for a while that the regulator is not going to, and a 4.7 on the input and a 4.7 on the output is not going to do justice to supply those spikes.
Well, the spikes that are causing us trouble, they're in like the 700 megahertz range.
Yeah, that's right. That's right. It's not we're not talking about 100 meg. But if you don't squelch that down on the output of the chip, there's no way in the world you're going to squelch it down on the inside of the chip. You've got to supply it clean. Now, what we used to do with the analog is we used to put either an inductor or a 10 ohm resistor in series with the 5 volt supply, because it was all 5 volt back then, so that went to the analog chip, so that you tried to stop the feedback from into the analog supply of all those spikes. So you're trying to keep this as quiet as possible on the outside so that the inside doesn't see the pulses.
Right. Well, okay, so this is like maximum torture test underway in this picture, right?
Yeah.
And you can see how much, and mind you, the digital scope's not perfect, right? But
No.
it's showing us that, I mean, this is 1 volt per division. So I'd say that's probably 200 millivolts of noise up there.
Yeah,
and
that's what you're showing down the bottom.
Yeah, maybe 200 down at the bottom, 150 at the bottom.
Yeah, in your digital signals, you show your digital readout down the bottom, the text.
So
it's showing.
This is what's on the bypass caps right as it heads into the pin on the chip, right?
Yeah,
So this is the
and
last stop on the circuit board.
Yeah, and that's not stable. That's noisy.
Well, it is, but look, I agree. It's not quiet, but this is, I mean, who knows? There could be more of an amp peak flowing here as we switch those pins, because those instantaneous turn on currents are super high.
Yeah.
And so, but you see this, let's say this is 200 millivolts, right?
Yeah.
Up at the top, that's 200 millivolts of VIO fluctuation. Okay, now let's look at XO. Now, XO is a 600 ohm inverter output, right? That comes from XI. So XI feeds in, it goes through just a single PMOS and NMOS inverter, which has about 600 ohms of intrinsic impedance, and it comes out on the other pin. So we wanted a low gain amplifier for the crystal so that it doesn't go into some overtone mode or something. So we can see the crystal is operating 20 megahertz. This is 10 nanoseconds, so there should be 5 divisions per cycle. So if we go here, 1, 2, 3, 4, 5. So this is 20 megahertz right here. But we can see this noise that's superimposed on here. And that noise is like 1 volt peak to peak, right?
Don't forget you've put a pile of capacitance on there, because your probes add to it. That's always an issue of trying to scope oscillators.
Right, well, this is 0.6 picofarad on these active probes. These are 1.5 gigahertz active FET probes. So
I've never used them.
So, and what I did, I'll show you, let's see. For the ground, here's one of the probes, right? Oh. Okay, so you see this here, this tip. This is the active probe, right? It actually gets warm, so it has things here to let the heat out. So this copper thing, this, if you can put my hand behind, you can see it.
Yeah.
This, okay, see that copper thing there? That's the ground, and I keep it touched to this body here. And then
Right,
the active tip is the 0.6 puff FET gate that gets amplified inside the probe. And this feeds back to the main machine. So anyway, this is a very tight loop here, right?
Yeah.
There's not a whole lot of room for funny stuff. So that's how I did these measurements. What we can see though is that there's a whole 1 volt of noise that is on this inverter output on XO.
Yeah.
And so either it's coupling on the circuit board, and there was some of that going on, right?
Yeah.
But this could also be reflecting what is going on with the internal power supply rails for those 4 IO pins, which are shared by XIXO.
Yeah. Yeah. Yeah.
Because when those transistors switch, it creates a huge current draw. And there is about 60 puff of bypass on those pads, if you add it all together, that are inside the chip. So there actually is bypass in the chip too. But what we're seeing here, I think, I calculated, that's like 700 megahertz, those rings. That is the loop capacitance package. That's the bond wire and the lead frame, right? And this package is from Amcor, right? It's this exposed pad package.
Yeah.
So the loop inductance on the package itself, due to the bond wire and the lead pin, ranges from 2.57 to 3.32 nanohenry. So if you mix that up with like 30 picofarad or 40 picofarad, the equation is 1 over quantity 2 pi square root LC. Okay, so if you use this, 3 nanohenry, 40 puff, square root of that, and then times 2 pi, take the reciprocal, you get about 740 megahertz. And that's
Bill?
pretty much what we're seeing here. That ring is 740 megahertz. So that voltage drop is probably occurring for briefly over the bond wire on the package.
Yeah.
So what we have is this like shock to the power rails internally inside the chip, because these massive IO pins are getting banged one way and the other, causing like local, momentary brownout conditions.
Yeah. Yeah. That's exactly what's happening.
Yeah, it's not.
Yeah.
It's not,
I don't know the internals of the chip. I couldn't possibly design a P2
yeah, you could.
or anything else.
You totally. Any of you could if you got into it. So here's.
Yeah, it takes years.
It does take time. Now here's what XI looks like, right? And so now there are protection diodes which are just sort of ever present on all IO pins, so that if the pin becomes, biased below or above the supply rails, it clamps, so it doesn't blow out the FET. So those diodes though are capacitive. So when the power supply, when ground and V plus and the power supply get banged around, this capacitively couples to anything attached. So in this case, we have the XI input pin, which just goes to an inverter. But you can see that noise on the power rails is coupling.
Yeah.
Now, let's see. This is XO. See, this is a 600 ohm output. So those pulses are shorter in duration, right? But if we go back to XI, this one, it's a little bit lazier looking because it's higher impedance.
Yeah.
So we're seeing the ringing occurring, but what's happening is here's why we're getting jitter. As this thing is oscillating in mainly a sine mode, there are these short pulses that sometimes are coincident with the threshold level, right where the 0 to 1 decision gets made. And then so what happens is the PLL winds up receiving like 2 edges or 3 edges where it should have received 1 edge.
Yep. Totally agree with you. I follow that through that. But what I'm trying to say is, let's make that power supply as quiet as possible. Yeah, let's fix the crystal as well, and do both. But do both. Don't do one.
Okay, right. Okay. Well, here's the thing, though. Look at this. We're going to go back to this picture. This is like 200 millivolts of noise, right?
Yeah.
Let's say we had an ideal power supply that was 0 millivolts noise on the outside of the chip, because we can only control what happens on the outside of the chip, right?
Yep, absolutely. Can't touch the inside.
Okay, we get it to 0 millivolts. Well, that could reduce this 1 volt of noise down to 800 millivolts of noise. But we're still going to have 800 millivolts of noise. And it's still going to be enough to destroy the function. It's still going to create extra pulses. Now let me show you another one. This is 50 millivolts per division. I don't have the radicals bright enough, but what you're seeing here is the difference from the negative to the positive side of the bypass cap. That's right at the V28, V31 pin. So at least I think that's what this was. I'm pretty sure. Which, actually shows less noise than the other one did. So this is saying here that we have maybe 75 millivolts of ripple across our input supply cap. And you know what? No, this could make sense, actually. If this is what's seen across the cap, remember, even the ground traces have impedance going all over the place, right?
Yeah.
So if we go back to this one here, if you subtract, what I did is I subtracted this from this, right? Because there's a lot of common modality here.
Yep.
So when we do that, we wind up seeing only 75 millivolts of ripple. So the cap only had 75 millivolts of ripple on it, which out of 3.3 volts is not much.
Yeah, I see your maximum is showing a 160, and it could be right at that point that you're getting your switching.
Let's see, where do you see this? Is it voltage peak to peak?
Yeah, there cursor's on it, yeah.
Well, that was probably when I attached the probe or something. Because I don't, this thing is so tricky to use. I got to use one hand to hold each probe, and then I got to get a kid to press buttons on the scope.
Yeah, we need an extra few arms and hands, don't we?
Yeah, because there's no way, there's no way to affix this probe. The whole situation is very delicate. So anyway, we had 75 millivolts, you could see here. It was never getting bigger than this on the screen. I just said, okay, hit the stop button, and she hit the stop, and okay, I took this snapshot from this camera I got. So then, now here is a picture of just the kind of noise floor of the same configuration. So I had the scope where I just touched the leads together. I touched the probe tips together, and then took a measurement just to say, like, what's the level of noise? So here it is touching, and that looks like, I don't know, maybe 50 millivolts per division. It's probably 25 millivolts peak to peak noise. And then we go over here and we get about, wait a minute, let me see, this is, I don't know, maybe that's, let's see, if that was really 50 millivolts per division, because it was in the math section of the scope. It wasn't the actual, 20 millivolts that you see here. This was 50 millivolts. So maybe that's 10 millivolts, 15 millivolts, right? And then when we go back to the measurement across the cap, we see a whole 75 millivolts. And you can see it's this, every spike here is when all those IO pins flip.
Yeah.
Now, here's the last picture to do with this. Okay, this is I AC coupled XI. I used a capacitor because that thing has only 100K to ground, that active FET probe, because they're probably trying to protect the FET, right? So this shows XI with the noise imposed on it, and one of those 4 pins toggling at well, let's see, if where it says 20 megahertz here, 19.9 megahertz, that's the crystal. And then we have these things running at, I don't know how many times as fast. Let's see, we've got 1, 2, 3, 4, 5 times as fast, 5 times the edges. And you can see that. Now, how do we explain this? We have this pin, this is what all 4 pins are doing. They're going down, then they're going up, right? And when we go down, we get an initial up spike, followed by a down spike, followed by like an up ring. So it kind of rings going the opposite direction. That's what I think is happening.
Yeah.
It's ringing in the opposite direction, and then the Q is not very high, so it settles down pretty quick. And so what I had to do is I had to make the thing that causes the pins to do, not every single clock, because it just becomes a completely muddled mess. You have to like put some spacer clocks in between so you can see what the event looks like in isolation. Otherwise, it just climbs on top of itself and looks like a mess.
Yeah.
So why are we ringing? Let's see, when the pins go down,
so when the pin goes down, you're not drawing the current, therefore the voltage goes up.
Yes. Well, but wait, we weren't drawing current either anyway, because these are all only capacitive loads, right?
Mm-hmm.
So
yeah, but you're still switching your pin.
Yeah.
There's not that there's much load, but you're switching a pin, and so you're getting a little bit of spike off an internal rail.
I think, let's see. Okay, so what happens to pull a pin low? You have to pull a gate high, right? So the output transistor gets yanked high on the gate in order for it to start coming down. And then both the N and the P, the gates go high, and that turns the P off and the N on, and then we have the pin going down. So the first thing that we're doing, let's see, for that thing to fly upwards would mean that the internal power rail went up, or maybe that thing was coincident with the beginning of the change. Maybe the drive current wasn't that high. It was only the main switching current later. Now the current to drive the FET maybe wasn't very significant. But it looks like it sets off ringing in the opposite direction of the pin movement.
Yeah, whether that's, and it looks like that's consistent, because if you look on the left side of that pulse, where it goes high, the ringing starts going low. But that's all dependent on what's switching inside the chip. Let's see if we can quiet it down on the power supply, at least as well. Because if you can get both, if we can get another bit out of our ADC, then that's a massive bonus.
Well, yeah, that'd be great. Now, when we're doing ADC stuff, you don't want to have anything noisy going on your neighbor pins like this, right? It blows up the neighborhood. So those are the pure ADC stuff is like a very quiet kind of relatively low power, quiet operation. So I would think our capacitor, what we do have for capacitors would be probably, I would suppose, first blush overkill for just doing ADC.
Yeah. I'm going to try and get, I'm trying to get find the,
Hey,
Chip, you said something when you were first moving into this next series of displays and showing us this final one. And that was, we're going to carry through, you said 7 something, even if we have a quiet power supply. And that was based on your bond wire RC, is that what you're saying?
Yeah, well, that ringing there is like 740 megahertz, which comes out to be the loop inductance of the package combined with the likely load on the IO pin, just a long trace on a board.
And so you're saying smoothing out the power supply takes us down, but only so far because of that package.
Yeah, what I was telling, Ray, is that let's see, if we go back, okay, we can look here at our rails, right? This looks like 200 millivolts or so of noise because it's 1 volt per division.
Okay.
But if you subtract out the local ground, these are two sides of the same cap.
Got you. We don't
here's
see
the ground.
we don't see the division marks that well.
I know, yeah, and look, the scope looks like it's orange, and you can,
Yeah.
and it's actually kind of white. I had to play with the white balance to get the screen to look
I'm with
right at
you.
all.
Scope looks from there though.
You know all about this.
Yeah.
So anyway, there's actually a net 75 millivolts of noise across the cap. And we can see that in this one here. This is 50 millivolts per division, and we're like a division and a half of vertical noise. You can look down here to see the graticules. So, but see, even ground isn't perfect, right? I mean, because of impedance of traces and whatnot, even ground is not absolutely, down to the millivolt ground. Everything is a little bit, it's not a concrete house. It's like a house made of sticks of wood and stuff. If someone walks, you can feel it in the floor.
Chip,
Yeah.
can you hear me?
Oh yeah, go ahead, Henrique.
Yes, please, when you look to the data sheet of Anchor, if I'm not, I can be wrong, but if I remember right, the ground is a two-step connection. First, from the pad ring, it goes to an intermediate ring, square ring of metal into the pad frame, then goes to ground in the exposed pad.
Right. That's right.
I'm not sure because we don't have an X-ray of an actual chip. But I don't believe that Anchor has chosen to only use the corner connections from that square pad ring towards the underneath exposed pad, because they are connected due to the extrusion of metal. But I've seen in other ships, mainly from Texas, that use a package almost the same, but with 4 huge metal protrusions that becomes another 4 pins of ground into the corner. I have taught you about that ship, that package in the past 5 years ago or 4 years,
Yes.
years ago. But in our package, I don't know what Anchor did when assembling. If they only used the 4 connections of metal into the corner to derive the ground from the square pad ring towards the exposed frame, or if they did, as in some other kinds of the assemblies of the same shape, they also do an extra connection using gold wires from the square pad ring, square ground ring towards the exposed pad. So we could have more loop inductance in our package than the normal package from the same line of Anchor, due to the way they connected the ground towards the exposed pad.
Right.
The data sheet, oh, please.
The drawing that I saw, so there is only one ground pad on our chip, right? It's the whole exposed pad on the bottom, which serves as a single ground point and as like a thermal release. So,
yes.
So there is another ring of copper that comes, that's folded up from the sides of that bond pad, where we jumper, which is connected to the ground pad. But oh, you're saying it's only connected on the corners.
Yes, the original I have seen.
Yeah.
The company that sold the IP, the intellectual property for that package to Anchor, they shared some IPs and exposed that situation to the stock market. Is not stated in the websites. It's stated into the SEC. The
Right.
SEC documents shows they are sharing some patents, and the patent for that package comes from another company. I believe it was from Japan, and that company originated the wireframe that is stamped in metal, and it's a 3-layer, not 2-layer, three layer. The top
Yeah.
layer are the pads you can see in the 100, 25 at each side of the propeller. The intermediate layer is 1 square of metal where the grounds are supposed to be connected from the pad ring towards that intermediate ground. And at the corners, you have 4 angular connections as a diagonal, but
That's like I'm drawing, right?
3D, yes, in 3D. The diagonal leads to the pad ring. But sometimes I see in other ships, Anchor chooses to also connect a lot of ground wires between the points where the grounds are coming from the pad ring towards the square ground layer, then drive another connection in gold towards the exposed pad to diminish the impedance.
Right.
So the real loop inductance for our package is some way unknown. We don't unless we have a note from Anchor that made some tests into the facility. We don't know exactly. It can be lower than, not higher than.
Right.
Our actual loop inductance for ground can be lower than the spec.
Right. Oh, wait, I didn't, you know what? I did this the wrong way. These should have gone to the die, not to the outside. So what Enrique is pointing out, that there's this big ground pad in the middle, and then they have this like stamped part that gets folded up to make this flat ring that goes around the perimeter of the chip. So it connects at the corners and then it jumps. I wrote these wires the wrong way. They actually go like this. They go from the ring to the pad.
Yeah,
The ring
yeah.
to the pad. That's how they work. Okay, not how I drew them at first. And so see, everywhere we have a VIO pin, either a core ground or a VIO pin, we also have a ground connection pad right next to that on the die. So wherever there's a VIO or a VDD pin, there's also a ground pin. So what we would do is we would jumper the, here's from the outside to where the VDD pin would go.
Yes, yes, exactly.
Yeah, so our current path is circuitous. It's kind of like it goes, from here down to here. Oh, wait a minute. No, it'd go from here down to down here, or it would go for a wire here. It would have to return back to these corners here.
Just near the edges of the sides of the exposed pad, there are a teeny area of metal that is not used by the base of the ship, of the silicon ship. In that area, I believe, I'm not sure because we don't have X-ray. I believe the Anchor did another group of connections to even lower the total loop inductance of the ground. So
Yeah, I think they would have had to because they advertise this package as being good for up to 2.5 gigahertz signals. So it seems that unless they were just looking at the short hops between the lead frame pins and the die and ignoring the ground.
yes, but
sure.
remember P2 die is way huger than normal for that type of package.
Oh, so we have,
The
yeah.
normal package of Anchor for that format is about 9 millimeters or less, and the silicon is expected to be 8 by 8 millimeters maximum. P2 uses more area, so they use the limit of the package to
Right.
create exposed pad.
Right. Yes. Well, yeah, that could be an issue too. That could affect all kinds of things. But what I did do is the IO or the ground that goes to the pads comes from that ground lead frame, because I didn't want to have separate, or how could I say this? I didn't want to have bulk grounds all over the chip, because what happens is as the core draws lots and lots of current at 1.8 volts, it's going to lift up ground and pull down the supply. And that would cause 30 millivolt offsets on all of our analog stuff. Therefore, they have their own connection to the main ground pad with a separate bond wire and no DC connection. But, okay, hey, Stephen Morocco. I was going to answer your question.
Sorry, I've lost you there. I'm with you now.
It happens to me all the time. Okay, so here we go. You asked, what is that? What was I talking about?
Yes.
You see here, we have 1 volt per division, right?
Yes.
And we have these spikes that are actually, I mean, if you look at this one over here, this is probably like 1.5 gradicules. That's like 1.5 volts. Okay, but then consider that across the package, I mean, going into the chip, we only have 75 millivolts of ripple. So the ripple's occurring on the inside of the chip. So what I was pointing out is that even if we got the ripple to 0 volts on the outside of the chip, we're still going to have maybe 1.5 minus 75 mils inside the chip.
Gotcha.
So there's only so much we can do. It's like a parent trying to herd their kid. They've only got so much control.
Yeah, but Chip, if you're able, it's not just removing the spike on the outside. It's the matter of being able to supply the current when it's required. And if you can't, so there is that. Going back to your pad design that Henrique was talking about was interesting, because you've got a very heavy, I'm presuming, ground frame running around the outside, as you would also have for your power supply, your 3.3 and your 1.8. So I'm presuming there's 3 big rings of metal running around the outside, and the inner one will be a ground.
There's one.
There's one. So
you pull it up real quick.
Okay, so you're just bringing your power pins directly into your die, okay? But you've got a nice ground plane running around, and even though you might have small diagonals going to that center pad, all your outside is heavily joined by a thick pad, which is what we do in a PCB. When you get down a little further explaining to Stephen, I'll show you my layout, my PCB layout of what I've done. And that sounds really interesting with the way you've got your pad, way the Amcor pad frame seems to work. Because I thought I had a downside in my ground plane, but that I wasn't able to overcome with 2 layers. But that sounds really interesting.
Yeah, okay, so, okay, here we go. Okay, here we go. Dual row, single row exposed. Okay, yes. Wait a minute, what is this? I'm looking at different packages. I'm going to move something into the window here. All right, let's see. How do I grab this? So I got to grab the whole thing. Okay, you see this?
Not yet. There it is.
So here we have the lead frame pins coming in, right? Here we have the thermal pad on the bottom, but this isn't actually this is not what we have. We have one contiguous pad on the bottom. And I think we have something like this. See this little step up here?
Yep. Right.
It doesn't work?
Yeah, works coming to me.
That's the power ring.
Yeah, no, you know what? Wait, what is this? No, this is Fusion Quad. Hold on, this is the wrong thing. I wanted something else. Hold on. Maybe I'm not going to find it here. What we have is simpler. There's just one stepped up region, and it is a ground. It's just for grounding. It's like a big ground ring, but I'm not sure. Let's see.
The package you were looking at, the Fusion Quad, is almost the same. The intermediate ring you were seeing in the cut is the ground, is the ground, the square ground that like a picture, the wood involved in a picture. This square ring is used to step down ground until the touches the exposed pad in the bottom.
Yeah.
The difference between that extra pads that package has is not important, because the rest of the package is exactly equal to our package.
Okay.
So Chip, what kind of capacitor is right next to the package? Is it a ceramic cap?
Yeah, it's an X5R, I think it is. It's a 4.7 microfarad, no, I think 6.3 volt cap.
Yeah, so that cap is going to have it's not going to have a very good ESR and possibly high ESL. So what I recommend is you put additional X7R caps on top. And one other thing is to, I know it seems crazy, but to add a little resistance, because that will lower the Q, and you will be able to see if you can affect the Q, the ringing, by adding more loss on the outside to lower the Q so you don't have the ringing.
Okay, I hear you. So what we would put the, oh wait, the capacitor or the resistor would go not between the cap, or would you put it between the cap and the pin, or would it go before the cap?
So you either use a capacitor that has deliberately more ESR, and this is just to test the theory out. You can use a tantalum, for example, that has more ESR, or you can physically put a small resistor in the ceramic cap in series.
Okay. I'll show you something. There's a lot of thought. Everyone's aware that you should add. Where'd my thing go? Hold on. I'm gonna have to close some stuff to recover. Here we go. Everyone has the idea that you should put often, well, in a case like this, smaller caps in parallel with larger caps, right?
Well, that was in the old school, that was really true. Nowadays, with these caps, it may not be as important.
How's it going?
Okay, so that's right. And here's the reason why I think. Because larger capacity capacitors typically were larger, they had more intrinsic inductance, right? So the inductance was what was nullifying the effect of the capacitance at high frequency. But when we have like 0402 chip caps, we have almost no inductance. I mean, a little bit, but I mean, it's negligible compared to what it used to be. So I have, do you see this? You see this graph here? This is a 0.1. Let me close it. Here we go. This is a 0.1 microfarad. This is an X7R, excuse me. It's X7R that we're using, not X5R. So X7R. Now you can see here, this is the ESR. And there's two things here. There's the blue is the ESR and the Z is the impedance, right? So the impedance troughs down here in the red and goes up. The ESR, well, let's just look at the higher number, the impedance. If you look at this graph, it looks like here's the one line. So it's probably 3 ohms right here, right? Does that look right?
Yes.
Okay, 3 ohms. We'll go down here, and this is about just a hair over 0.1 ohms. So the blue is 0.1 and the red is 3, right? And this is at 1 gigahertz right here. This is 1,000 megahertz. This is a gigahertz right here. So watch this. Now we go to, this is a 0.1 microfarad. Now we go down to the cap that we're using. And look at this. This is a 4.7, right? 475. It's, oh no, this is an X. Let's see, this is
X5R.
X5R. Okay, same thing, X5R. So check this out. At 1,000 megahertz, at a gigahertz, our Z is still at 3. And our ESR is still at 0.1. It's maybe even a little bit lower than it was in this case. It's about the same. But isn't that pretty interesting?
It is, but if you put two of those in parallel, you're going to change that graph and you're going to lower it.
Yeah, that is true. But there's no disadvantage to using, well, my whole point is there's no disadvantage to using a 4.7 than a 0.1. You might as well take the extra capacitance in the same package if you get equivalent ESR and Z.
Yeah, I'm not totally convinced that everything is in those graphs that is what happens in actual fact, but that's the gut telling me that, not specifications telling me that.
So Chip, one thing you can try to have the same capacitance, but the pads are much longer, so the inductance is less. Are you aware of those caps? So the form factor, just imagine this cap, instead of putting the ends where they are, imagine if the ends were put on the broad side.
Yeah.
Oh, okay. So it's
I went to try that on my board and I couldn't fit the pair of tracks in between it.
Yeah. But the thing is, just to try it out, if you swap it out for those, and if you go to an X5R, which should be more lossy, so it will have more resistance, I think, and see if those can affect the transients you see inside, and then it'll give you a clue that, you know, is it from outside you can affect it, or no, it's all internal. That's all I wanted to say.
Okay, but I think if we're seeing on this high-speed scope, if we're seeing a net 75 millivolts, or maybe even a net 100 millivolts of ripple on, oh wait, let me move the, go back over to this picture here. If this is our net voltage across the cap, it seems that we're pretty low, right? We're at 100 millivolts out of 3.3. That's 3% ripple of the whole voltage across the cap, which is not perfect, but it shouldn't be enough to allow that 1.5 volt.
Yeah. So what that tells me is your ESR is very low. So, and that will make your Q go up.
So the ringing goes up. The frequency
Exactly. So if you have, you would definitely have more ripple here if you have a higher ESR cap, because the ripple current times that resistor would create a bigger drop. However, your Q will go down and maybe you won't ring as much. So it's just something to try to see. Maybe you can affect it from outside.
I see. Okay, yeah. So what we want to do is, okay, we could get rid of the, we could quash the ringing a little bit. And then because here's what the whole problem manifests right here, where we start getting, well, that's actually XO. This is XI. This is the crystal input, right? See the crystals running. I think all these spikes are common mode on both XI and XO, right? But at these points internally, it starts to register extra pulses because of this. So if we stopped it from ringing, do you think we could stop it from getting 2 extra edges where it should only see 1?
Absolutely, because the other modes of coupling is you could have the bond wire inductance could be coupling to each other and or capacitive coupling inside the chip. So anything you can do to reduce this resonance in the first place is going to help across everything.
Okay, that's interesting. That had never occurred to me. Yeah, this is like, I know some kinds of things don't like ceramic caps. I think there are some switchers that really, some rely on their low ESR, but in some cases, I remember historically, it was a problem because the ESR was too low, because it would cause probably traces on circuit boards to do this too much.
Yes, those are LDOs. Don't like it because they depend on the zero created by the ESR to actually stabilize. So they need a tantalum or a electrolytic, and ESRs make them oscillate.
Wow, okay. I wonder, so what would happen? What we're going to get, I mean, when we have that big turn on inside the chip that causes this instantaneous current surge that results in all this LC ringing. I'm trying to imagine what would it look like? It would, because it is a short, it's going to cause a short-term, somewhat of a brownout inside the chip, right? When this event occurs.
Yeah, depending on the inductance, if it's too large, it will collapse, like you said, the voltage would collapse. But you know, if you just reduce the Q, hopefully it won't ring as much, maybe.
Yeah.
That's an interesting thing you're talking about, because my board's it's not using LDOs as such. They're a much higher dropout, which probably means that there may be not the ringing because I've not used a really modern LDO. Be interesting to put the scope on my board, see what's on those pins as well, Chip, and just see whether there's a difference.
Yeah, I think this ringing though is occurring long after the regulator. It's occurring between the final bypass cap at the pin and the internal power rails of the chip. The voltage regulator's already done its work, I think, and now we're just seeing a phenomenon between the last bypass cap,
yeah,
the power and going into the power pin, and then what's happening inside the chip.
Yeah.
What Reza is saying is we can reduce the Q, stop that ringing. We can stop these multiple things. But I think there's still going to be some kind of unfriendly activity on XI though. Yeah.
Yeah. But you've got to attack. My thought is you've got to attack the supply in the first place, and if you can then minimize the ultimate effects of it. But the problems from my point of view is that I think it's getting into the chip from the supply and coupling, and what you're seeing as an effect. Now, that doesn't mean there isn't some things you can do to minimize those, and we've certainly seen that there is, but you've got to minimize everything. I'm going to have to duck out shortly. Do you want to have a look at how I laid out the board, the
Yeah, sure. Let's take a look at that. Let me stop sharing here.
Okay.
By the way, if this was an issue with the regulator, the control loops are in the 10 or 20 kilohertz. And at this response, the only thing is the capacitors and the inductance of the package. It wouldn't be the chip. So just the reference.
Because that's kind of what I think too. These frequencies are so high and they're occurring, it's all after the regulator. Because the regulator doesn't make 740 megahertz ripples.
No, but if your regulator can't handle it, and that's what one of the big things they've talked about with these really fine LDOs, and you've got such a tiny little chip in there, and it's trying to supply one thing, whereas I've got a big regulator supplying all the pins. So I can supply a bulk piece when it's needed. This is my, can you see my board?
Yeah, that looks good.
Okay, so if you look down here, let's go down to the appropriate section we're looking at. So there's my crystal coming directly in to there, and you can see I've got a big point between it, but you can see I've got really short leads.
Yeah.
Here's my 3.3 of the, this is the one we're really talking about. So the 3.3 is coupled to the pad, right at the pad. If you can see as I zoom in, that distance there is 5 thou. So that this little ring here is a guard ring of 5 thou. So you can see my pad is 6 thou away directly to the 3 volt.
Yeah.
And as I go down now, the other side of that, you can see I've only got 5.5 mil, 5.5 thou to the pad for my capacitor. So that capacitor is right on the pin. This is a bypass cap. So this is the 0.1, the 100 nanofarad. And you can see I've got a ground wire on the inside of the chip, of the pad. Now that's a ground ring that runs around the outside. Now if I zoom out and turn a couple of these things off, I want to turn the off. That wasn't the one I wanted to show. Right, so this is my ground pad around the frame, and you can see I only come out around this way to get across to those, and they're on the underside, the underlayer. So my ground is effectively isolated around there, which was what I thought was interesting with the Amcor pad, that they would go diagonally, because there was no way I could get through on a 2-layer board from a ground that's running down there back into the ground here without going around the ends. Now, if I flip over to the green, this is a bottom layer. So there's my ground layer. This layer here is, I think it was the 1.8. And then my 3.3 is around the outside. So I've got big heavy traces running around the board. But the downside of this is that I don't have a huge amount of copper on the underside of the board to get rid of the heat. So, but everything's a trade-off when you're doing a 2-layer board.
Yeah. Well, that's great. You packed that.
But I'm finding that my 3.3, my 1.8, I've got 3.3 regulators on my board. They're SOT 323s. So I pre-regulate the 5 volt down to 3.3 and then immediately into the 1.8 regulator. It doesn't supply the 3.3 to my board. For the 3.3 to my board and the P2, I have a SOT 89, which is a smaller regulator for 3.3. And it's interesting, I have roughly the same heat dissipation in the main 3.3 to the 1.8. The 1.8 the 3.3 sot 89 and the P2 all get to around the same temperature. So I balanced it much better than I could have ever hoped by pure ace, so to speak. So because I didn't know that when I built the board exactly how they'd compare.
That looks great. I don't think you can do much better than that, especially the 2 layers.
Yeah. So these are all
You're
my
kind of
ground.
muffled.
These are all my grounds pads from those capacitors around it. All these pins here,
Yeah.
and you can see how I alternate the 3.3 and the 1.8s drop to the opposite side.
Now, how do you get ground only comes into the center pad from the top then, right?
Yes, yes, yes,
Can you
it does.
show us those pads again? You probably got lots of small pads.
Sorry?
You probably got lots of small pads for ground.
Chip, your
To-
audio's getting
Chip, I think
messy.
something happened to your microphone.
Oh, it fell into my lap. Here we go. Sorry.
I wonder why it was getting so quiet and having trouble.
That's better.
Yeah.
Okay, so now we can
So
see
he-
your ground.
Yeah, so here's the top. So, you know, basically all these wires here are bringing it to the back to the top layer.
Right.
And then but this is how I'm coming out, and there's nothing I can do about it. I tried like hell to get these corners bigger, but there's nothing.
Yeah.
You can't do anything about that. You're limited. But I've got extra wires here as soon as I come out to get it to the layer, get it to the other layer. And these are the rings. Now, as I said, these are all 100 nanofarads. But on the 3 corners, this is my 4.7 mic. That's doing the 1.8, so that's a bulk capacitor on the end. This is a bulk capacitor on the end for the 3.3, and I've got that in each corner of the 3 corners. I don't have it in the 4th corner. So my bulk capacitors are sitting at the 3 ends. And directly coupling to that frame. So this is the coupling into the frame. So a much heavier track, but it's a compromise because I don't want to upset my ground either.
Right.
But of course, that was not possible in this corner. I couldn't get, I wanted to get a bulk capacitor in there. There just isn't sufficient room.
That looks good. Michael Mulholland, are you hearing any of this? I wonder what you can say. Like, I think our board pretty much, well, we have more ground planes. And so we have more escapement, but I think as far as doing the power here, Ray, I don't think it could have been done any better. And in the ground, you just can't do, there's nothing you can do beyond getting it out of the 4 corners.
No, and this is the 1.8 coming in, and I've got another 4.7. I think that's actually might be a 22. I'd have to check. Might be a 22 mic. And this is the output of the 1.8 regulator. And I've got a 0.1 and a 22 mic. So a big bulk capacitor.
Right.
And this is the SOT 323 regulator. It's being pre-regulated by this 3.3 coming in. It only comes directly straight into the pad here. There's another capacitor sitting in here somewhere. I think it's across here.
Okay.
I bring a bypass. I've got a bulk capacitor rather. So, and the input here, that's actually the output. I've just got an additional one as well as this side. Same here. This is the little SOT 89. And once again, coming in, I've got a 22, and going out, I've got a 22 and a 0.1.
I see. Yeah, that's good. That was designed with power in mind first, and then just get the signals out.
Yeah, yep. And while we're on it, because, whoops, that was a bit silly. But there it is. This is the SD card. Remember, there's been all sorts of people having problems with SD cards. Part of those problems is they don't have the proper caps across the connector. And as close as I can get, because this opens out, the closest I could get was here. And there's two capacitors here.
I see.
A 0.1 and I've got a 22 or a 4. I think I got a 4.7 across there for a bulk. And these pins here, when I flip underneath on, that's where I've got my flash chip. That was an afterthought. So it's grabbing it's using the same bypass caps. There aren't any extras on there, but it's coming direct from, the power's coming direct from this section here. So it's pretty close. Not perfect, but pretty close.
Well, that's that looks pretty good. That's amazing that you got all that in 2 layers. And I don't think it could possibly be done any better. I don't know what else you could do.
Where I stuffed up was when I had to expand out to get my pads out, I ended up with all this extra space because originally I laid all of this out on to go on a 1.1 inch square daughter board. When I expanded it back out, I had space and I didn't expand these out. This is 50 thou pitch. That's the pull-up resistor required for the for booting off the flash chip. This is my link to enable the onboard reset circuit for the transistor reset. And I didn't expand this out. And you see I've got the space to do it, to make it a 50 thou pitch. It's only a little jumper set for using Kynar wire, 26 gauge wire to select the link. And it would have been nice to have it on a jumper. So.
Well, that's a great example of how to do a 2-layer board. I didn't know that was like a reasonable goal, but I guess it can be done.
Yeah. Well, Peter's done his on a 2-layer board, the P2D2.
Yeah.
He hasn't got as many bypass caps on there. And really, mine's an overkill, but I thought, well, at least if I put them in there, I can aim for the quietest board. I can always remove them one at a time, but I don't really have the test equipment to see the difference. Although now with this little test that Roger did, I'll be able to tell whether it's getting noise back in as I take them off. But that's what I did. This, by the way, these are the 6 pins that I don't bring out to the external world. So they're on little vias we can put Kynar wire on. So I thought, managed to squeeze them in there to be able to get them out, so that if someone really wants to use those pins, they're there.
They can get in there.
Yeah. And I managed to get, while we're on it, I managed to put on there the 2 micro USB connectors, which connect to the 4 other pins that don't get brought out, so I can put a USB keyboard and mouse on there as well, just with a adapter cable, which you can buy for $1.50 off eBay. So I can use Gary's USB driver for that.
Yeah.
So, yeah.
Okay, well, super. That looks really good. Hey, would you be interested? I don't know how closely you want to hold that thing, but that's a good example to put up for here's how to do a 2-layer board and handle the power, and because the power is a huge issue in routing this thing.
Yeah. I don't know. I have to think about that one, Chip. I definitely haven't published any of my older boards.
Yeah,
with
I mean,
the,
it wouldn't
with the
even.
layouts.
I don't even think Gerbers are necessary. Just pictures of like, look, here's a way. Because if someone approaches this chip for the first time, They're probably going to
Yeah.
be, they're going to have to work all these things out. If they see
Yeah.
something like this, it just all snaps to grid right off the bat.
Yeah. Yeah. Let me think about it. I'll probably
All right.
be okay, but I got a few other things on my mind at the moment.
But whatever you want to do, it's yours.
Yeah. But yeah, we've got to get this chip performing absolutely the best it possibly can,
Yes.
because we're going to have enough uphill battles trying to get people to look at it. If we
Right.
can make the thing perform even better, if we manage to snavel another 1 bit out of our ADC.
Well, yeah, that would be great. You know how to conduct a test for ADC, right? I mean, there's a lot of ways you could do it, but what I always do is I run, well, it's kind of a silly test. I don't use calibration because that's just there's too much involved in that and it's slow, but I just take continuous readings of, say, like a super slow moving sine wave, and I look at like the crests, and I see, is it stepping by one value, or is it jittering by 2 or 3? And that's kind of how I've always just checked it out.
Yeah, I no longer have any of my decent test equipment, which is one of the reasons why I'd love to build and I played with code to do it, a logic analyzer with the P2. I mean,
Yeah.
with that board, I can stick a board on top of the board, and one could monitor the other. But with the multiple cogs we've got there, we can actually monitor it internally.